Thank you, Wes, and thank you for everybody for coming today to hear about some of the work we've been doing in Southern California on the San Andreas Fault. And I just want to acknowledge my co-authors here. The lead on this study was my PhD student, Ryley Hill, who's now at Los Alamos National Lab, and then primary collaborators who contributed a lot to this study are Tom Rockwell in paleoseismology, and Yuri Fialko for geodesy and modeling. The central question here is focused on the Southern San Andreas Fault. It's the most hazardous fault in California, and we think it's locked, loaded, and about 100 years overdue. This paper proposes that ancient cycles of a large lake, a much larger lake than you see here in the background of this slide, on top of the fault, modulated the timing of past major ruptures. And I just want to acknowledge for the Earth Science New Zealand folks that I hope that you'll appreciate the fault and fluid coupling here and how hydrologic loads, natural here, but also potentially anthropogenic, can interact with critically stressed faults. I overlay here in the foreground our finite element numerical mesh, and actually, I don't know if you picked up on that, but we are right looking down the strike of the plate boundary, and that big red line there is the Southern San Andreas Fault. And this work was published in the summer of 2023, and I hope that you'll appreciate that this talk really integrates paleoseismology, quaternary geology, and also coupled numerical modeling. So it's genuinely an interdisciplinary study. Yeah. Okay, so first I'll talk a little bit about the motivation, and then I'll talk about some background work related to paleolakes and paleoseismology, the numerical model itself, and then some results and implications. I just want to telegraph the central result early. We do think that hydrologic loading increased the Coulomb stresses by several hundred kPa, and fault stressing rates by more than a factor of 2 above the tectonic background. And we think that it was sufficient for modulating the earthquake cycle. The Southern San Andreas Fault fits into a larger network of faults in California. It is actually the fault in California that poses the largest seismic hazard. It's actually a historically quiescent section of the SAF system, so there's no large earthquakes in the written history of California, which we consider sort of somewhere in the range of 1750 CE. So it makes it a uniquely dangerous fault because the elastic stresses have accumulated at least for the last 300 years. We know that geodetic data from Fialko 2006 shows about 18 millimeters per year slip rate, and that's fully locked from the surface down to the seismogenic depths, down to the basic crust at 15 kilometers. So the entire seismogenic zone is storing this elastic strain that has to be eventually released in an earthquake. And if it were released in an earthquake, the hazard would be immediate. So this portion of the fault can produce, we think, upwards of a magnitude 7.8 and affect potentially up to 25 million people living in this region. So just some background specifically on the Southern California region. You see here on this map different faults and splays of the Southern San Andreas system shown by the red lines here. The Pacific Ocean out to the west, you see Los Angeles. Where I'm from, San Diego, is underneath the inset map showing you where you are in California. But the important fault here, and as I don't know if you can see my cursor on the screen, the important fault that we're interested in here is the Southern San Andreas, the portion of the Southern San Andreas here that's outlined by this sort of box. And this, we'll talk a little bit about this Coachella site, which is a paleoseismic investigative site. So this fault lies, our study region is the Salton Trough, which is this large structural basin, pull-apart basin, that is about 300 kilometers long and marks the southern terminus of the Southern San Andreas system. Interestingly, one side of this trough, this big bathtub, is formed by the delta of the Colorado River. So the Colorado River here forms the boundary between California and Arizona and typically discharges into the Gulf of California, but there's a big delta here. And sometimes it avulses to the north, and actually the Colorado River has drained into the trough. In modern times, that forms the present-day Salton Sea in the early part of the 20th century, but in historical times has filled a much bigger ancient lake, which we call ancient Lake Cahuilla, and you can sort of see the ancient boundaries of that shoreline here. The last major rupture on the Southern San Andreas is marked at about 300 years. And what's interesting about this site is that because we have this a record of lakes and desiccation, we have the perfect situation to actually measure organics in these lacustrine sediments and potentially date ruptures. And that's actually been done by a number of groups. One of the notable studies is by Philibosian et al. In 2011, which established the benchmark paleoseismic record for the Coachella Trench. 7 major earthquakes over the past 1,000 years, with an average recurrence interval of about 180 years, plus or minus 40. A quasi-periodic distribution. The current open interval is about 300 years, so close to a factor of 2 of the mean recurrence, meaning the fault is statistically overdue in its window by most recurrence models. Now, of course, these are PDFs, so we don't have exact dates, but we have some idea of when these earthquakes occurred. Rockwell et al. 2022 is going to improve on these PDFs and narrow their uncertainties, and that's going to be part of the leap forward in this work. One other thing I want to mention is that this has been a noted open window for the last 40 years. Famously, in 1986, at the AGU conference, Carrie C. said the Southern San Andreas Fault is 10 months pregnant. And 40 years later, the fault still hasn't ruptured, underscoring frankly, how poorly we understand what controls rupture timing beyond simple recurrence statistics. And it's not just that the fault is overdue by typical statistics. Mechanical models calculating Coulomb stresses say that the secular tectonic loads are well above any reasonable failure threshold. So this is the sort of paradox. And our hypothesis is that past ruptures required maybe a hydromechanical nudge, maybe from this lake that's currently absent. Okay. So the question mark here that I put onto the slide says we know the fault is overdue, which is sort of strange at first glance because we think that the recurrence intervals are somewhat quasi-periodic. If past earthquakes were preferentially occurring during maybe lake high stands, and now we're in an extended dry period since we haven't had a lake since the early 1700s, does the absence of a lake partly explain the current quiescence? That's the question we're trying to answer. And the possible answer is related to this lake. So we know from paleoseismic evidence that there's a correlation between lake high stands and previous earthquakes in the region. This has been documented by Waters in 1983, Garola and Rockwell in 1996, and Philibosian et al. In 2011, but it's never been rigorously modeled with the fully coupled approach that I'm going to show you here. Prior modeling work, such as Luttrell et al. 2007 or Brothers et al. 2011, other papers that have investigated similar sorts of ideas, did not take this fully coupled approach. So I'll talk to you about that in a little bit. So how did we reconstruct the Paleolake history? Well, this was a lot of work. In 2022, Tom Rockwell, who's shown here, pictured next to my graduate student Ryley, out in one of the field sites at Salt Creek, which is shown here. It's field site number 3 on the eastern side of the modern shore of the Salton Sea, actually where that drone image in the first slide was originally taken. This paper pulled together radiocarbon dates, more than 100 radiocarbon dates, I think like 122 radiocarbon dates, from organic material in various trenches, both and also drowned tree stumps on the lake bed floor, and lake sediments across the entire inundation zone to try to build a 2,000-year lake history from these various sites across the inundation area. 6 distinct lake high stands are now well constrained over the past 1,100 years, and we label them lakes A through F, each lasting decades at high stand and separated by roughly 50-year desiccation periods. This improved Paleolake chronology is what made this study possible. Earlier lake histories had timing uncertainties that were much larger and essentially made it difficult to correlate lakes and earthquakes. Part of the insight of this Paleolake reconstruction was a reinterpretation of what the shallow or small, thin organic material layers meant in some of the various locations in the inundation zone. In our reinterpretation, these organic rich layers represent key stratigraphic markers that actually are abundant shoreline debris. So as the lake is rising, and we've observed this in real world cases like here in Laguna Salada, as the lake rises from a desiccation period, it pulls in essentially detritus and other dead organic material that floats to the shoreline and is deposited at these various shoreline sites. So therefore, the radiocarbon ages from these organics date material that was growing in the preceding dry period and not necessarily dating the lake high stand itself. So the organics ages give a maximum age constraint for the ensuing lake inundation. Okay. All right. One other key piece of Paleolake information are these buried trees, the dead stumps of trees that grew below the shoreline and were covered with shells or lake deposits. These tree stumps in growth position are unambiguous evidence of lake inundation. The trees grew below the shoreline elevation and were killed when the lake rose. So if we can radiocarbon date these dead trees, we have some additional evidence of the timing of lake inundation. And then finally, we also have some idea of when pluvial periods on the Colorado River existed over the last 1,000 years. So these pluvial periods also add an additional piece of evidence constraining the timing of when lakes possibly occurred. We need pluvial or wet periods to cause avulsion and therefore start filling the lake. So how are lakes and earthquakes intertwined? Well, our interpretations, our earthquake horizons are mostly unchanged from Philibosian et al.'s 2011 paper, but 6 of the past 7 earthquake horizons lie within lacustrine sediments. So therefore, the main difference in earthquake ages are a result of reclassifying which sediments are lacustrine and assuming that organics are from material that grew within the lake boundary during dry periods. What this means is that many of the past earthquakes, 6 of the past 7, occurred when the lake was present in our interpretation of the last 1,100 years. If you plot them on the same graph, so here's a PDF of our interpreted earthquake probabilities and their timings, and also the timings of lake filling, high stand, and desiccation from lakes F through A, going back all the way to 930 CE, you can see that there's a visual correlation, and it's a key observational result. If you just did some simple Monte Carlo statistics on these 2 distributions, you would find it very unlikely that this happened by random chance. But correlation doesn't establish causation, and this is why the physical model is essential, because the physical model helps to establish causation through a physical mechanism. I'll also note that our interpretation from the Southern San Andreas data is also found in other parts of the Southern San Andreas system. So some of the splay faults that I might have mentioned, I don't know if I mentioned them at the very beginning of the talk, the Imperial Fault, San Jacinto, Southern San Andreas. So we see this across the basin, not just locally at this major Southern San Andreas site. So the physical mechanism part, what am I going to invoke? Well, I'm going to come from my background, which is really, as Wes said, is in groundwater modeling, but focused on addressing the hydromechanical problem of induced seismicity in Oklahoma. and apply those skills and physical mechanisms to this idea, connecting lake loading and stresses on faults. They're essentially, one way to look at this is through a Coulomb failure criterion. So we're looking at essentially stresses resolved onto a fault. And in order to make a fault slip, you can potentially increase the pore pressure, therefore decreasing the effective normal stress on that fault. Or you can increase the poroelastic stresses and potentially bring that fault closer to failure. So you can do you can do both. You could do both at the same time, or you could do you can do both at the same time. Okay, so let me just, for those of you who aren't familiar with poroelastic theory, let me just give you a little primer on how this works. So imagine you have a poroelastic crust and you have a load on that crust. At time t equals very close to 0, you have what's called an undrained response, because essentially the load is flexing the crust and a physical weight. There is compression on the crust that increases pore pressure in this sort of fashion everywhere underneath the load. With time, that undrained response diffuses. So essentially, if you just had an undrained system, that initial undrained load would be highest at the beginning and diffuse over time away from the lake or from the load. At the same time, you also have a drained response, which means that independent of the undrained load, you also have diffusion from the bottom of the lake, because now you have higher pore pressure, and that diffusion is also increasing pore pressure. So these two competing sort of poroelastic mechanisms, you can have the undrained part and the drained part. They sort of work together at sometimes, and undrained response is more commonly important in the very beginning, and the drained response is more commonly important later on. So the combined sort of situation produces essentially some sort of undrained and drained response at a long time interval. And just to show you how this might, at a sort of first order scoping model, I'll show you some results from a simple analytical solution. This is from Roloffs et al. In 1988. So this is a very old and well-known problem of a periodic load on a poroelastic medium. The general solution looks something like this. I'm not going to belabor that point. But let's imagine we load this crust in this 1D analytical solution with lakes of the character and timing that we've proposed in our revised Paleolake and Paleoearthquake model. So we can plot the pore pressure evolution with depth in the both the undrained and drained cases for these various lake high stands across the 1100-year period. And this is sort of like a toy model. It's sort of giving us some idea of what we might expect in a larger 3D simulation. And there's already a lot of good information that comes out of these first order scoping models. So on the left, you see the pore pressure change for a diffusivity of 0.01 meters squared per second. And it's a little bit hard to see, but initially there's the undrained response, essentially the response right at the base of the lake load. And that occurs very quickly. So it ramps up very quickly. If you look deeper into the model, so increasing Z is in kilometers here, you'll note that there are different curves. And those curves represent the competing influences of the undrained response initially, and then the diffuse drained response later. Okay. One important thing that came out of running these models is that we started to see that there was a memory effect at the seismogenic depth that we think these earthquakes nucleate, which is somewhere around 7 or 8 kilometers. You can see that, and that's the bottom curve here, that the timing of when the lake is on and the timing of when the pore pressure or stress increases at depth, at the relevant depth, is delayed due to the poroelastic material. And in fact, if you run a cycle of lakes, you can see that in between the lakes, it's not the stresses at depth are not fully recovered from some background state. So there's some memory in this system beyond just the time window of the actual lakes itself. So there's a cumulative nature going on here. After 3 or 4 lake cycles, the baseline pore pressure at depth is significantly higher than the start. And I think this amplification could make the difference between a fault failing and remaining stable. If you just looked at a single lake, you wouldn't see these sorts of effects. Okay, so let's talk a little bit about the model, the larger model that we ran. One of the reasons why we want to run a 3D simulation is that it's going to be able to capture a realistic fault geometry. It's going to be able to capture heterogeneity in the stratigraphy, and it's also going to be able to capture the coupled mechanics and hydraulics that we think are important. So here's a picture of our modeling domain, a finite element mesh, 600 kilometers on each side, 50 kilometers deep. This is a very large model. We also are going to be modeling not only the crust, but also the mantle, because there's also viscoelastic things happening that affect the stresses on the fault at this sort of scale. Initially, there's going to be no flow between the crust and the mantle layer. Surface has no displacement or pore pressure boundary conditions. Equilibrium stress and pore pressure are assumed for the initial part. And then we're going to be loading this system with our Lake Cahuilla. An important piece of our model is the internal fault surface that represents the Southern San Andreas Fault. We're going to use a dip of this surface as 60 degrees from Lindsay and Fialko. This is inverted from geodetic data. Interestingly, a strike slip fault is dipping at 60 degrees. Here it is. And that has an important implication for how the stresses resolve on our fault at depth. We're going to vary the fault's permeability by roughly 3 or 4 orders of magnitude at least, with 5 different permeability structures. And that's going to represent a permeable damage zone. One thing we learned from seismicity, induced seismicity in Oklahoma that can occur 4, 5, 6 kilometers below the injection zone is that damage zones, permeable damage zones of critically stressed faults are very important for transmitting pressure and stress to depth. And that is one of the key features of the model we want to capture. We also have some hydrostratigraphy of the sedimentary formations overlying the basement. These are based on Thompson et al. 2008. And if you're interested in some of the properties of this model, you can see them here. And the most important model uncertainty is the permeability of this fault. And we're going to vary that permeability from 10 to the minus 14 meters squared down to 10 to the minus 18 meters squared, or basically no damage zone that's different than the intact crystalline basement at 10 to the minus 18 meters squared. Okay, so here are some of our results, and I'll walk you through what these results look like for an individual lake cycle, and then we'll look at the whole picture and time series of stress on the fault. So let's look at the results from the first lake cycle, and we're going to just plot stress change from 0 to 1 megapascal from blue to red. So at the very beginning of filling of Lake F, which it takes about 18 years for the lake to fill based on Colorado River flow rates and the size of the lake, there's very little pore pressure occurring at depth. And the view, I should mention, the view we're taking on this is a weird cross-section. We're looking at it from the mountains to the northeast and looking through the fault back at the lake, okay? And so what you're seeing here is the sedimentary formations down to a certain depth, and then below that, the crystalline basement. And I think it'll become clear where the fault is once I show you some pictures moving forward in time. So this is right at the beginning of the lake. And what you can see is that there's very little pressure or stress change on the fault and very little stress change permeating into the basement. But by the end of the lake filling, so by 9:30, in this case, you can see pore pressures in the sedimentary formation reaching close to 1 megapascal. You can sort of see it spreading out across the sedimentary formations and maybe not permeating very well into the intact basement, but you can now start to see the effects of the fault damage zone pulling pressures or allowing pressures to diffuse to seismogenic depths, even by the end of the first lake filling. By the desiccation of Lake F, you see sort of pressures are modulating, but they're not returning to the background levels, right? We are at an elevated pressure condition of around 0.5 CFS. And you can also see that there's remaining or leftover stress from this Lake F before the start of Lake E, something we saw in the analytical model, but is bearing out again in the numerical model. We refill this lake by 1007 CE or AD, and actually now pressures are even more elevated in the basement and spreading out more widely because of the elevation of pressures from the previous lake. And so this is an important phenomenon. We think that when you have this sequence of lakes, you have this memory effect where the subsequent lakes are building on one another. Okay, one other key piece of this, if we look at just the fault and the change in CFS underneath on the fault, it's not just that there are positive CFS changes to depth along the fault right underneath the lake, but also outside the lake because of the ability of the fault damage zone to transmit fluid pressures along it. So pore pressure is the dominant force driving positive CFS changes. The changes in shear stress are relatively less important for driving the CFS change. And this is a critical point because previous work had mainly focused on the elastic stress component, not really concerning itself with pore pressure or the diffusion of pore pressure down a potentially permeable damage zone. Okay, so let's look at the temporal correlation of delta CFS and earthquakes. So here, plotted here are the various models of fault damage zone permeability, from the highest being model 1 and model 5 being basically a model that does not have a damage zone. In all 5 of these models, we see positive delta CFS during the lake high stands. And this is the most important result, I think, supporting our triggering argument, because I mean, there have been past studies that have shown that delta CFS was actually negative during some of these lake high stands, and that was purely the result, or mainly the result, of the elastic stress changes, not the pore pressure. If you have a higher fault permeability, you get faster diffusion, larger peaks, and more distinct cycle-to-cycle patterns, whereas if you decrease the fault permeabilities, it's a little bit more smoothed. The cumulative stress buildup across the early lake cycles from lakes F to E to D is, I think, very clear. Then there's a little bit of a desiccation period, and then the three most recent events, C, B, and A, with the most recent event occurring in the early part of the 1700s, also show this same sort of effect. I also want to highlight a threshold. And that threshold is this dashed line of 0.1 MPa Coulomb failure stress. This is a common triggering threshold from decades of earthquake interaction studies. We know from Southern California, King et al. In 1994 from aftershock triggering, Talwani 1997 for reservoir-induced events, and then from our own work in Oklahoma over the past decade, that 0.1 MPa is a pretty common triggering threshold to start seeing earthquakes related to CFS changes. In addition, I also want to compare not just the magnitude of delta CFS and its timing, but also the rate of CFS change. Now, the tectonic loading rate is 16 kilopascals per year. And if you imagine the mean recurrence interval is about 180 years, that means there's about 3 megapascals being built up between each earthquake. 0.5 or 6 MPa is roughly 15 to 20% of a full earthquake cycle's worth of stress built up in a single lake filling event. So that just reiterates the point that it's not only the magnitude, but the rate at which these CFS changes are being imposed that we think is quite important. And in fact, if you directly compare the lake's CFS rate change to the tectonic CFS rate as a function, as a ratio, with one being essentially the two quantities being equal, we see that in the filling phase of these various lakes, that the lake's stress contributions could be a factor of essentially 2 or 3 times at max the tectonic loading rate. And in induced seismicity studies in Oklahoma, we know the earthquake rate, and thus the earthquake probability, is directly related to the rate at which we stress the reservoir and therefore the faults. And so even maybe more important than the absolute magnitude of CFS rate change or CFS change is the actual loading rate of these lakes. It's very, very fast compared to the tectonic loading rate. One other thing I want to mention is some general sensitivities. We also considered faults of different geometries. Strike slip faults we tend to think of as being mostly subvertical. In this part of the Southern San Andreas system, we think it's about 60 degrees. But if you change it to something like 50 or resolve stresses on a 70-degree fault, it will modulate the amount of CFS you see at depth, but not so much that we would reverse any finding of this study. And then one other model sensitivity we ran was the mantle viscosity. So if you have relaxation times anywhere between 20 and 200 years, it can change essentially the resolved Coulomb stresses on the fault. But in our case, it did not fundamentally change the sign or the magnitudes of the CFS rate changes we observed. Okay, so some conclusions, and I also want to talk a little bit after this about some implications. The physical model confirms that there's a correlation, that the paleoseismic correlation, I think, has a mechanically sound basis. And we think that increases in lake level result in positive Coulomb stress changes on the Southern San Andreas Fault, bringing it closer to failure. The lateral diffusion of pore pressure along this 60-degree dipping permeable fault zone, combined with this poroelastic memory effect, I think emphasizes the importance of this added model complexity. And our model predicts that predominantly negative Coulomb stress changes will occur for sufficiently long dry periods. So a gradual decline in Coulomb stress changes from the present open interval as the Salton Sea level continues to decline is a potential reason why we've seen some additional quiescence or maybe an overdue Southern San Andreas Fault. One thing you might be wondering is, do we see this in other parts of the world? And I would argue we do. Other natural and anthropogenic places we've seen this is the reservoir impoundment case in China, the Zipingpu Reservoir, about 100-meter deep reservoir, potentially linked to the 2008 magnitude 7.9 Wenchuan earthquake, where the reservoir loading in that case was modeled to be much smaller than the delta CFS we're modeling on the Southern San Andreas. And then also another transform fault, the Dead Sea. There's a paper out talking about orbital and metalineal scale changes in lake levels, facilitating potentially earthquakes and landslides in the Dead Sea Basin. And then finally, because I'm talking to folks here in New Zealand, I also wanted to bring up some New Zealand related things. And I found this paper from Andy Nicole and others in 2024 in Seismological Research Letters. Very good, very nice statistical study. A strong contrast to Southern California. So actually in New Zealand, they looked at 80%, they looked at 50 active faults within New Zealand, and they found that 80% actually have elapsed time intervals since the last earthquake less than their recurrence interval. So most faults in New Zealand are actually not overdue. They're right on track. And they explain this very nicely through looking at the essentially distributions, the probability distributions of the elapsed times, and show that it's just more likely that you're going to be observing intervals shorter than the mean than you are to observe very long tail, rare, long intervals. So that sort of pulls the mean up, mean recurrence time up. I think this is an explicit contrast to California strike slip faults. And actually in this paper, they argue that instead of using mean recurrence, we should use maybe something like median recurrence times that wouldn't be as affected by the distribution of elapsed times. And in that case, for Southern California, that would only serve to increase the overdueness, because essentially our recurrence interval would drop if we use the median. So with that, I will pause and just direct you to the paper, and